Hello guys, this is Code in Code and this is another video lecture for this is I guess the first lecture for strongly connected component, and in this lecture we are going to study about the Kosaraju's algorithm for strongly connected component. So before we start, we must know what is we are going to study about. So we are going to study about strongly connected component, and what are those? Strongly connected components are subset C of vertices such that for any two vertices in the set C there exists a path between them in the original given graph. So C is the subset of the subset of original vertex set of the graph, and C is such that for every two node in set C there exists a path from V to U and from U to V. Now if I show you example, here you can see for this directed graph there are three strongly connected component, and of course strongly connected component is defined for directed graph. For undirected graph it is simply connected component. There is no strong notion of strongly connected component. Now here you can see there are three strongly connected component. These three vertices consist of a single connected component. This forms a single connected component. These four vertices form a single connected component. So in total there are three connected component. Now here if you see, if you choose any two node out of these two, there exists a path from one to another and another to the previous one. Basically if you choose these two nodes, there is a path from 1 to 3, as you can see this is direct, and also there is a path from 3 to 1, and there it is. So any two nodes you choose from a subset or from a strongly connected component, then there is a path between them. This is called strongly connected component, and the problem is to find how you are given a directed graph, how you would find and report how many strongly connected components are there, or even in some cases you might be asked to print each connected component, the vertices of each connected component. For example, for first I'll be printing the list of these three nodes to indicate these three form a single connected component, then the second list would be this, the third list would be this. So this is the problem that we are considering in this lecture. Now strongly connected component and the transposed graph. Now you might already know what is a transposed graph. So assume this is the original given graph, given directed graph, and the transposed graph is simply the original graph, where basically transposed graph is the graph where the vertex and edge vertex set is the same, only the edges are reversed. So if in the original graph there was an edge from 2 to 1, then in the transposed graph the edge would be from 1 to 2. This is simple concept, right? Now you might have studied a little bit about Kosaraju's algorithm, which is used to find strongly connected component. It uses two DFSs. In the second DFS, if you pay attention, it runs DFS on the transposed graph. What is the reason for that? You will know in a moment when I'll be finishing this lecture. But first thing, the most important thing, why we one of the reason why we run DFS on the transposed graph is this. See, in the original graph, this forms a single strongly connected component. These three nodes, this forms separate strongly connected component. Now these four form single strongly connected component. So in total there are three strongly connected component in this graph. Now if we take a look on the transposed graph, the strongly connected component does not change even in the transposed graph. So 1 2 3 were forming a single connected component in the original graph, and so they are forming in the transposed graph as well. 1 2 3 are still in the same connected strongly connected component. Similarly 4 was forming a separate strongly connected component in the transposed graph as well. It is forming a separate SCC. Now in the original graph, these fours 5 6 7 and 8 were part of a same SCC. Now even in the transposed graph they are part of the same SCC. Now this is one of the properties why we use transposed graph, and the main reason you will know in a moment. So the transposed graph has the same strongly connected component as the original graph. So this was more of the story. Now the important thing about Kosaraju's algorithm, for proof, to understand the Kosaraju's algorithm in detail, you must know about the condensation graph, because this helps us to prove why Kosaraju's algorithm actually works. So what is a condensation graph? A condensation graph is a graph made up of strongly connected component of a given graph. For example, here you see the blue dots represent the vertices and the black edges represent the edges of the original graph. So blue vertices and black edges represent the original graph. Now you see here these yellow circles, these represent vertices of condensation graph, and these yellow arrows represent edges of condensation graph. So each strongly connected component of the original graph acts as a vertex in the condensation graph. So these 5 nodes form a single strongly connected component or single SCC. That is why in the condensation graph these are forming a single vertex. Similarly, for this SCC, this SCC, this is. So in the original graph there are 6 SCCs, and that is why there are 6 vertices in the condensation graph. Now the edges, how the edges are defined in the condensation graph is that there is an edge from SCC Ci to SCC Cj. Basically, assume, let's take an example of these two. So there is an edge from one connected component, one strongly connected component to other strongly connected component, if and only if there exists a node V in Ci and U in Cj, and there is an edge from V to U. So basically, in the condensation graph there is an edge from an SCC I to SCC J, if and only if in the SCC I there is a node V, and in the jth SCC there is a node V U, I guess, yes, U, and there is an edge from V to U. Since here from this strongly connected component there are 2 edges going out from this to this, that is why in the condensation graph there is an edge from this SCC towards this SCC. Similarly, why in the SCC there is an edge from this SCC to this SCC? Because in this SCC there is a vertex from which there is an outgoing edge towards this strongly connected component. So now you got the idea what are the edges and the vertices in the condensation graph. Now you might think how this can help us. Believe me, this is one of the most important thing to understand before going to prove Kosaraju's algorithm, why that works and what is the building block of Kosaraju's algorithm. This is the building block of Kosaraju's algorithm. Now that we know that what is a condensation graph, now there is an important property of condensation graph, that is condensation graph does not contain any cycle in it. You can simply prove it. Now see, to prove it, what you can do, assume that there is actually a cycle. So in the condensation graph, remember, suppose in the condensation graph there is a cycle. We are claiming that in the condensation graph there does not contain any cycle. The condensation graph does not contain any cycle. This is what is our claim. Now to prove that, you can simply prove it using contradiction. So assume that there is a cycle. Let's say there is a cycle between these 4. If there was a cycle, then these 4 would form a single strongly connected component, not multiple strongly connected component. Why is that so? See, if it forms a cycle, then that means there is an edge from this SCC to this SCC, and this to this, this to this, this to this. That means from any node in this SCC you can reach any node to this SCC using this edge which was there from this SCC to this SCC. Similarly, from any node of this SCC you can reach any node of this SCC. How? You can simply follow the path of the cycle, right? That would mean that these two are in the same strongly connected component, because from any node of this SCC you can reach any node of this SCC, or from any node of this SCC you can reach any node of this SCC, which basically says that there is a path from every node of this SCC to this. And similarly for this, that indicates that these two must not be, these two should be a single connected component, single strongly connected component. But this contradicts the fact that these two are actually 2 different strongly connected components, and hence the assumption that we made that there exists a cycle is wrong. You can try and prove it if you haven't understand what I have said, but you can also Google. I think I'm in fact sure that you will find 1 or 2 links on the Stack Overflow proving that condensation graph does not contain any cycle. So condensation graph does not contain any cycle. Now the question is how this information is helpful to us. Well, this is one of the most important and the helpful information you will know in a moment. So first of all, for the graph, now if there are two strongly connected components Ci and Cj, and there exists an edge from Ci to Cj, then out time of Ci would be greater than the out time of Cj. Now what is out time? We have in the graph theory part 1 we have already discussed in time and out time using DFS. So here you see the upper number, basically the numerator represents the in time and the denominator represents the out time. Now here you see this forms a single strongly connected component and this forms a single strongly connected component. Now out, as you might remember, in time and out time is defined for a vertex. It is not defined for a connected component or for a strongly connected component in this matter, but we are saying that the out time of this is strongly connected component, right? But we have already seen that in and out time are defined for vertex, not for the SCC, so we need to define them. So what is out time? Out time is the time when you leave a vertex from DFS call, right? When you enter a node for DFS call, that is your in time, and when you leave that node out and your DFS basically completes the execution and you leave that node, that time is known as the exit time or out time. So out time of SCC would be of course the maximum of all of the out time of the nodes which comprise of that SCC. So this SCC is made up of 1, 2 and 3 vertices. So maximum of out time of all of these 3 is 6. It is having 4, it is having 5, it is having 6. So of course maximum is 6. So out time of this connected SCC is actually 6. Out time of this SCC is 12, right? So what the claim is that the lemma is that if there are two strongly connected components which are connected, and there exists, connected means there exists an edge. So if there exists an edge from SCC Ci to SCC Cj, then out time of Ci would be greater than the out time of Cj. This is the claim. If there is an edge from A to B, then out time of A would be greater and out time of B would be smaller. This is the claim. Now what is the proof? Well, just a second, let me see whether I have yeah. So I need to give you an example. Example is this. See, so suppose you made a DFS call to any of the node in this SCC, right? So see, this is SCC, suppose this is A and this is B. There is an edge from B to A, so of course the out time of B would be greater than an out time of B would be greater than out time of A. This is the claim. Now why is that? So see, there is two conditions. First, either you make a DFS call to SCC B. I think I have called this B, right? So either it is possible that you first made a DFS call to B, and then if you made a DFS call to B and A, it is possible that B and A both will get visited by that DFS call. Or the other condition is that you first made a DFS call to any of the node of SCC A. So let's explore both of the condition and prove that in both of the condition, no matter whether you make a DFS call first in SCC B and then to SCC A, or when you make a DFS call first to A and then to B, it doesn't matter. In both the condition, since there is an edge from B to A, so out time of B would be greater than out time of A. Now let's go with the first condition where I have made DFS call first to any node in the SCC B. Now if you make a DFS call to any node in SCC B, all of the node will get visited because this forms a single SCC, and whenever you make a DFS call to any node in a single in a SCC, then whole SCC gets visited. So when you suppose you made a DFS call to this, so from here you can reach here, and then from here you can reach here. Now you try to make a recursive call to here, but this is already visited, so you would go here, and then you would go here and here. Now you try to make a DFS call to this node, but this is already visited, so what would happen? You would leave. So this the first node we are leaving is this, so this would have the least out time among all of these 6 nodes because we are leaving this node first, and then this, and then this, and after leaving all of the nodes, will come here and then leave this node. So you are seeing all of these, the execution of all of these nodes have been completed. Then we are starting to leave each node of SCCB. Clearly these nodes have been the DFS call from these node have been already exited. Then we are exiting from these particular nodes. So we have left these node earlier before we are leaving this node. So of course the out time of this node would be greater than the out time of this, and hence out time of this SCC is greater than out time of this. So this is the condition where we make DFS call first to SCCB. Now there is another condition in which we first make DFS call to this SCC. Now since there is no edge from this SCC to this SCC, when you would make a DFS call to this SCC, all of these nodes will get visited and none of these nodes will get visited. So once these nodes have been visited, and when you make a DFS call to this any of the node in this SCC, because once you make a DFS call to this SCC, any node of this SCC, whole SCC will get visited and you will return to main function from where you have made a DFS call to any node in this SCC. And then after completing this, you would make another DFS call now to this SCC. You try to make a DFS call to 2, but 2 is already visited. You already remember how SCC works, right? From main function, we run a loop from 1 to n, and whoever is not visited, we make a DFS call to that. First, we made a DFS call to 1. 1 makes 2 and 3 also visited. Now we return back to main, and then we see whether 2 is visited or not. Yes, 2 is visited. And then we see for 3. 3 is already visited. Now we see for 4. 4 is not visited, so we'd make a DFS call to 4. So now what is happening, all of these nodes have already been exited. I do not know whether that is a correct term, exited or not. We have already completed the execution of DFS here, so the out time of all of these nodes have already been defined. Now after that we are making DFS call to this, so of course the out time of these nodes would be greater than them. So in both of the condition, the out time of that strongly connected component, which if there is an edge from A to B, then out time of, if there is an edge from A to B, then what would happen, the out time of A would be greater than the out time of B. All of the pieces of information that till now I have given, I have summarized them here, and all of these are building blocks of Kosaraju's algorithm. One of the most important, in fact these all are the most important thing to understand Kosaraju's algorithm, the working of it, and to prove why that is correct. First we have seen that okay, the original graph and the transposed graph have the same strongly connected components. Second, we have learned about the condensation graph. Third, we have looked at the property and we have proven that the condensation graph are actually acyclic. Basically they do not contain any cycle. Fourth, we have seen that if there is an edge from Ci to Cj, then out time of Ci would be greater than the out time of Cj. These are what we have learned till now. Now one important thing, see, in a DAG, that is directed acyclic graph, there will be at least one node which is having degree 0. So if you are having a DAG that is directed acyclic graph like condensation graph, if you are having a condensation graph or any DAG, then there would be at least one node with in degree 0. Now what is the proof of it? I'm not going to prove that. I'll be putting the link of the proof from Stack Overflow. This is one of the proofs where we have someone have asked how to prove that if you are having a DAG, then there exists at least one node with in degree 0. And as you can see, this is an accepted solution, and this is a pretty straightforward proof by contradiction. So I'll be putting the link of that into the description, so you can actually go there and see why, and you can look at the proof. It is easy to understand, very easy to understand. You can go there and read the proof for this claim that a DAG has at least one node with in degree 0. Now this is very important condition, and I'm going to show you why do I have this. Yeah, one important, see, if when I'm making a DFS call to any node, you already know if you make a DFS call to any node, all of the nodes which lie in the same strongly connected component as that node to which you have made DFS call, all of those will get visited. Basically, these three form a single connected component, single SCC. So if no matter whether you make a DFS call to 5 or 6 or 7, all of these three will get visited. That is because all of them are reachable from each other because they lie in the same SCC. So of course, when you make a DFS call to even a single node of SCC, the whole SCC gets visited because of the nature of because of the recursive nature of DFS. Now, wouldn't this be a helpful situation if you make a DFS call to certain SCC and only those nodes which lie in that SCC, only those gets visited? Wouldn't that be helpful? Let me tell you what. If I make DFS call to 5, I want only 5, 6 and 7 to get visited. If that happens, what I can do, I can make a list and count the total number of SCC. From main function, I made a DFS call to 5 and then I made a list. I went to 5, I inserted 5 into the list, then I made a recursive call to 6, then I also inserted 6 into the list, and then I went to 7, I also inserted 7 into the list, and then I can go to 4. But what I am saying, try to understand, I want to do something that only those nodes get visited. When I make a DFS call to certain node, only those nodes get visited which lie in the same SCC as that node. So if I'm making DFS call to 5, I want only 5, 6 and 7 to visit it. But the problem here is that when you make a DFS call to 5, 5, 6, 7 will get visited as well as 4 and 3 because there is a path from 4 to 7 to 4. So recursively, 7 would make a DFS call to 4 and 4 would make a DFS call to 3, 3 would make a DFS call to 1 and 2, and the whole graph gets visited. But I do not want that condition. I want only those nodes to get visited who lie in the same connected component. So I want the DFS to stop after reaching 7. Somehow when I make DFS call to any node in this SCC, only these 3 nodes get visited. If that can happen, then we can in fact make a list of all the SCC and we can count the total number of strongly connected component, right? Now that is where this information comes into the picture. There is a node which is having, not a node, there is a, now I'm talking about DAG. And what is DAG? DAG is actually what we say, condensation graph. Condensation graph is actually DAG, directed acyclic graph. If condensation graph is DAG, then what would happen? There would be at least one node in condensation graph which would have in degree 0, right? There is no edge which comes towards it. So if you make a condensation graph out of this would make a single vertex from which there will be an edge to this, and from it there will be an edge to this. So this would form a vertex, this would form a vertex, this would form a vertex in the condensation graph, and there would be an edge from this to this and this to this, right? So you can see in degree of this SCC is 0 because in degree of this is not 0, there is an edge from this to this. In degree of this is not 0 because there is an edge from this to this, from this SCC to this SCC. So I'm talking about condensation graph for this. Just imagine the condensation graph. If not, just use your pen and paper and try to make a condensation graph. Would be very easy because this is only 3 node condensation graph. It is basically a bamboo. Now you see this node and this node of condensation graph are not having in degree 0, but this is having in degree 0. If this SCC is having in degree 0, that means there is no edge coming towards them. There are only edges which are going outside of this strongly connected component. What would happen if I talk about the same strongly connected component but in the transposed graph? What would happen, since in this strongly connected in this original graph the in degree of this is 0, then in the transposed graph out degree of this would be 0, because in the transposed graph in degree converts to out degree converts to in degree. Now since this strongly connected component is having 0 in degree, that means in the transposed graph this strongly connected component will have 0 out degree. And do you understand the importance of 0 out degree? The importance of 0 out degree is that when you make a DFS call to any of this node, the DFS is not going to leave this strongly connected component. That is the importance of having 0 out degree. You see, when you make a DFS call to even 5 would make a DFS call to 1 would make sorry, it is 7. 5 would make a recursive call to 7, 7 would make a recursive call to 6, and that is it. You are not going outside the strongly connected component. See, this is the power of 0 in degree, and this is the idea of Kosaraju's algorithm. So what would happen? First, we will see in the original graph which strongly connected component is having 0 in degree. 0 in degree will exist because we have proof of it, that DAG, since we are talking about the condensation graph, which is a DAG of the original graph, and since this is a DAG, there would be at least one node, basically one strongly connected component, which would have in degree 0. If in degree of that strongly connected component is 0, then in the condensation graph, then in the transposed graph, that strongly connected component will have out degree 0. If that strongly connected component is having out degree 0, that means when you make a DFS call to any node of that strongly connected component, the DFS call is not going outside that strongly connected component, and you are able to visit only those nodes which lie in that strongly connected component, and that is important. So I would make a DFS call to either 5 or 6 or 7. The whole strongly connected component will get visited, and I have a list of 5, 6 and 7, and I know there exists a strongly connected component which comprises of 5, 6 and 7. Now I would remove all of this node from the original graph. Now I would again find a node which is having in degree 0 in the original. So I have removed this strongly connected. After finding out that these 3 form a single strongly connected component, now I would remove these 3 along with all of the edges from the original graph. Now this is having 0 in degree after removing this strongly connected component. Now since this strongly connected component is having 0 in degree, in the transpose this would have 0 out degree. I would make a DFS call, and the list would contain only by 4. So I have 2 lists of strongly connected component, 2 lists of different strongly connected component. One comprises of 5, 6 and 7, another comprises of 4. So now I know there are 2 strongly connected component till now. I would also remove 4. Now there is only one edge and it is having 0 in degree. So of course in the transposed graph it would have 0 out degree. I would make a DFS call, and all these 3 nodes will get visited, and I will have a third list with myself with the nodes 1 to 3. Now I know there are 3 lists, so there are 3 strongly connected component. If someone asks me to print each list, I can do that too. So see, all of these that we have studied, there is a condensation graph, there is DAG with 0 in degree and so on. All of the things that we have learned have led us to a solution, to an algorithm which actually gives us information about the strongly connected component, and this is the building block of Kosaraju's algorithm. This is Kosaraju's algorithm. Now why we use 2 different DFS, I'll be telling you in the next lecture, because this lecture is already going too far. I mean, it is too lengthy, I believe. So in the next lecture I'll be explaining why we need 2 DFS. In fact, how you would determine, okay, this strongly connected component is having 0 in degree. How you are going to decide that? Because all you have is a data structure. All of the edges are saved inside. The whole graph is saved as adjacency list. How you are going to decide which strongly connected component is having 0 in degree? How you are going to do that? Of course, that is a problem. So Kosaraju uses 2 DFS. First, to determine the order in which we need to run DFS in this transpose graph, so that each time when you make a DFS call, a successful DFS call, it tells you a single strongly connected component. First DFS would create an order of the nodes in which we should make DFS call into the transpose graph, and the second is of course making actual DFS calls in the transpose graph and finding the strongly connected component. I hope this lecture was helpful, and of course I'm assuming that this have given you enough information that you can even try to understand Kosaraju's algorithm by yourself if you even read from certain sources. So I hope this was helpful. If this was helpful, please let me know in the comment section. So this was all for this lecture. Thank you guys for watching, and in the next lecture I'm going to explain both. Basically I'm going to show you how Kosaraju's algorithm is implemented. So this was all for this lecture. Thank you guys for watching, and till the next video drops, keep coding. Thank you.